All right, let's proceed to item number 21. In how many ways can a committee composed of four boys and five girls be chosen from a group of seven boys and 10 girls? Okay, let's see. What's your answer? Let's see if you got this. So take note that order here does not matter. Order in a committee, I mean, order does not matter. So this is a combination problem, not a permutation problem. So out of the seven boys, you will choose four of them. So seven combination four, which is 7 factorial all over 7 minus 4 factorial, 4 factorial. This is the number of ways to determine, uh, which is, by the way, 35 for the four boys out of the seven. And out of the 10 girls, you will choose five. So that's 10C5, which is 10 factorial all over 10 minus 5 factorial, 5 factorial, which when simplified becomes 252. And by the fundamental counting principle, we have to multiply 35 and 252, and this gives us 8,820 ways in all. I hope you got this. 22. There are seven black and eight white balls inside the urn. They are identical in all aspects except for color. If you intend to draw five balls at once, in how many ways can you draw at least three white balls? So you could draw either three white, four white, or five, all five white. And the number of black balls would also adjust depending on the number of white balls. Okay? So here we have actually three cases. The first case is, remember, out of the eight, you will choose 8C3 here. You could have three white, and you remember you will get five balls. And if you have three white, it's understood that you will get two black. So 8C3 is a number of ways that you could get three white out of the eight white balls and two out of the seven black balls. By the fundamental counting principle, we have to multiply 8 combination 3 and 7 combination 2. And this is our first case. The second case is having four white and one black. That's why you have 8C4 times 7C1. And the last case is if you have five white and none of them are black. And simplifying such, 8C3 is actually this one, this, and this one, this. This, so this becomes 56 times 21 for the first case, 70 times 7 for the second case, and 56 times 1 for the third case. And simplifying everything and adding gives us 1,722 ways in all. I hope that you got the gist of the explanation, and be very careful with your multiplication and division, okay? And your four fundamental operations in general. 23. Consider the 5 by 3 rectangle as shown. And you could see there's an X sign here in one of the 1 by 1 squares, inside the 1 by 1 square. How many rectangles contain the X symbol? What do you think? What's your guess? So there are many ways of doing this, and I'll just give you one way. And one way is by assigning numbers. Let's call this 1. And we will move this time from 1. Let's go to the left. 1, 2, 3, 4. So it could either have this until 4. If you go up, 1, 2. From here, if you go down, 1, 2, 3. And if you go from this spot going to the right, that's 1, 2, 3, right? And by the fundamental counting principle again, you have to multiply these numbers at the very end. So multiply 4, 2, 3, and 3, and that gives you 72 rectangles that contain the X spot or the X symbol. All right? I hope that you got this. Let's move on to item number 24. In how many ways can Jillian invite at least one of his 6 friends to attend a party? Remember, at least one, you could invite either 1, 2, 3, 4, 5, or 6. This means that there are 6 different cases, and these cases should be added after determining. So 61 is the number of ways that for you to invite 1 out of 6. 62 is for you to invite 2, exactly 2 out of 6, and so on until that you invite 6 or all of them. And by using the combination formula, you can verify this on your own. 61 simplifies to 6, then 62 to 15. Then you have plus 20, plus 15, plus 6, plus 1. And this actually is equal to 63. Hence, there are 63 ways for you to invite at least one of your 6 friends. But this is quite long, a bit long, slightly longer. So let's have a shorter one. In fact, it's actually a theorem that if you have NC1 plus NC2 plus NC3 all the way until NCN, it's just equal to 2 raised to n minus 1, where n is the total number of objects. You have to subtract 1 because this is the number of ways for you to choose nothing. Okay, so there's one way for you to choose none out of those objects. So 2 raised to 6 is 64. Subtract by 1 because that one case is you will take nothing, and that still gives you 63. So you see, we have 2 different approaches, but still the same correct answer. 25. How about this? How many positive integers with 5 digits or less that have a digital sum of 9? Digital sum of 9 means that the sum of all its digits is 9. For example, if you have the number 40,113, it is one of these because 4 plus 0 plus 1 plus 1 plus 3 equals 9. Okay, let's observe some patterns because by means of observations, we could actually simplify this rather complicated problem. So for example, let us represent each number accordingly with a number of dots and plus symbols. For example, if I have the 5-digit number, I represented 4 with 4 dots, plus 0, so no dot here, plus 1 dot, plus another 1 dot, plus 3 dots. So here, how many plus symbols do you see? You could see 4 plus symbols and 9 dots, right? But remember, according to the problem, you could have less than 5 digits. So let's say 4 digits. And if you have a 4-digit number, in this case, it could be safely presumed that the 10,000s place is 0. And using again a similar principle, that's 0 plus 3 dots plus 2 dots plus no dot plus 4 dots. Again, there are 4 plus symbols and 9 dots. If you choose to have a 3-digit number, we could safely presume that the 10,000s and the thousands place are both 0. And still, you could see that's plus 0, none, plus none, plus three dots, plus three dots, plus three dots. Again, there are four plus symbols and nine dots. In any number that satisfies the condition, there are always 13 objects. That's nine dots and four plus symbols. Hence, you could have 13 combination nine ways. Or you could also have 13 combination four because they are just equal with one another. Or to make the long story short, you could have 13 factorial all over 4 factorial, 9 factorial times 4 factorial all over 0 factorial, 4 factorial, which simplifies to 715 times 1 or 715. You might be asking, sir, how come 13C9? The explanation here is out of the 13 objects, 9 of them will be taken by the dots, and there will be 4 objects left and 4 combination 4. Or to make it simpler, you could directly go here because you have 9 identical dots and 4 identical plus symbols. That's why 13 factorial is divided by 4 factorial, 9 factorial, which simplifies still to 715. Okay? I hope you got it. 26. You have 8 flowers and you intend to put them to vases only, to 5 vases only. In how many ways can this be done if each vase should contain at least 1 flower? Okay? All right, let's see. From here, since each vase should have at least 1 flower, then there are 8 minus 5 or 3 flowers that may be placed in any vase. Here we have the assumption that each flower, that you will place 1 flower to each vase first. And that's why if you do, 3 flowers may be placed in any vase just to be sure. And in this case, we are sure that any vase will have at least 1 flower. Some will have 1 and some could have more than 1 flower. So let's call the 5 bases V sub 1, V sub 2, all the way until V sub 5. So we will distribute the 3 remaining flowers. So let's say 1 flower plus 1 flower plus 1 flower plus no flower plus no flower. Remember, you are going to distribute only 3 flowers. It's also possible that none plus 1 flower plus none plus flower. It's also possible that the 2 flowers will be placed in the first vase plus none plus none plus none plus 1. And if you could see in any possibility, here we have 4 Fs and 3 plus symbols. That's a total of 7. Here we also have in the second possibility, you could also have 7 symbols of which 3 are flowers and 4 are plus symbols. In the third case, again, 7 symbols with 3 flowers and 4 plus symbols. So therefore, to make the long story short, out of the 7, you will choose 3 that are flowers, so 7C3, and which means that the 4 remaining ones will be be taken by the position of the plus symbols. And this simplifies to 7 factorial all over 4 factorial, 3 factorial, times 4 factorial all over 0 factorial, 4 factorial, or that simplifies to 35 times 1, or simply 35. Or to make the long story short, since there are 7 objects in all, you can just go directly to this step here. 7 factorial, and since you have identical objects, 3Fs, so divide by 3 factorial, and identical plus symbols, so divide by 4 factorial. So you see, it will still be 35. 35. All right. 27. Let x, y, and z be positive integers. How many ordered triples x, y, z are there such that x, y, and z is, or the product of x, y, and z is 30? Take note, order here it says ordered triples, so order matters. For example, 1, 2, 3 is different from 2, 1, 3. Because now the moment that you interchange or you have a different arrangement, that is a different ordered triple. So we have to note that they are different. So 30 could be expressed by the product of three different numbers, 1, 2, and 15, right? So you could have 1 to 15, and there are three of them that are different. That since order matters, so there are three factorial ways or six possibilities or six ordered pairs. For example, 1 to 15, that's 1. 1, 5, 1, 15, 2. You could have 2, 1, 15, 2, 15, 1. You could also have 15, 1, 2, and 15, 2, 1. So those are the six possibilities. In a similar manner, 30 could be expressed as 2, 3, and 5. And since you have three of them that are different, they could be arranged again in another 3 factorial or 6 ways. So you have another 6 ordered pairs there. Remember, if you could see, I mean, there are no other three different numbers. There are no other three positive whole numbers that when multiplied becomes 30. So what we have to do is we have to add the total number of ways in these two cases. So 6 plus 6, that's a total of 12 ordered pairs. Okay, so far so good. 28. Andy plans to arrange 3 different mathematics, 2 different science, and 4 different English books by stacking them in a pile. What is the probability that all math books are together? So here, we have to note that there are 9 books. That's 2 plus 3 plus 4. And since they are all different, so there are 9 factorial ways to arrange all of them. Now, suppose the 3 math books are M1, M2, M3. The 2 science books are S sub 1, S sub 2, and the remaining are books are English, E sub 1, E sub 2, E sub 3, E sub 4. The math books have to be together. So let's put them inside the box, and they will be treated as one slot because they have to be together. So how many slots are there? That's 1, 2, 3, 4, 5, 6, 7 slots. And in these 7 slots, you have your 7 factorial ways, but the 3 of these math books could still rearrange themselves in 3 factorial ways. And since order matters, so I multiplied 7 factorial with 3 factorial. So 7 factorial, 3 factorial ways to arrange the book such that all math books are together. And if we talk about probability, classical probability, so it's a total number of favorable outcomes, which is 7 factorial, 3 factorial, all over the total number of outcomes, which is in this case 9 factorial. So the denominator, I express 9 factorial as 9 times 8 times 7 factorial. I stopped with 7 factorial because I know that I could divide the 7 factorials here into 1. The 3 factorial is 6. So this becomes 6 divided by the product of 9 and 8, which simplifies to 1/12. Did you get 1/12? 1/12? If you did, congratulations. But if not, it's a learning experience. 29. 5 fair coins are tossed at once. What is the probability that at least 3 heads come out? Pause the video and try this if you wish. Let's see if you got this right. Okay. Suppose now, by the fundamental counting principle, you have 5 slots for the 5 coins, and each coin could have 2 outcomes. That's why you have 2 times 2 times 2 times 2 times 2. or 2 to the fifth, or 32 possible outcomes in all. There are, in this case, the first case is for you to have 3 heads. And of course, since there are 5 coins only, of course, the other ones should be tails. So you have 5C3 for the 3 heads, and the remaining 2 have to be tails. So 5C3 times 2C2, this 5C3 is 10, and 2C2 is 1. This simplifies to 10. Remember at least 3 heads. You could also have 4 heads and exactly 1 tail. And using a similar manner, that's out of the 5, you will have 4 heads, so 5C4. And the remaining 1 coin should be tail, so 1C1. So 5C4 simplifies to 5, and 1C1 simplifies to 1. So 5 times 1, there are 5 ways for you to have exactly 4 heads. And the last case is if all the coins show heads and no tail. So therefore you have 5C5, and the remaining one is 0, combination 0. 5C5, all heads, and none of them tails. 5C5 is equal to 1 because if n is a natural number, n combination n is 1. And remember that 0 factorial all over 0 minus 0 factorial, 0 factorial, 0 factorial is equal to 1. Be very careful. 0 factorial equals 1. It's not 0. So you have one way to have exactly 5 heads and no tails. And since you have 3 different cases, you have to add them, giving us 10 plus 5 plus 1 or 16 possibilities to have at least 3 heads. But as using a similar reasoning, 16 possibilities out of 32, 16 favorable all over the 32 total outcomes, and that simplifies to 1/2. Hence, 1/2 is the correct answer for problem 29. I hope you got this. Problem 30. There are 6 and 5 distinct points in 2 segments as shown. If any 3 points will be chosen and be connected to form a triangle, how many possibilities are there in all? What do you think? So take note, it's not good to get any 3 points on the same line. For example, if I focus on this line, if I pick JID, this will not form a triangle because again, you need 3 points that are not collinear. Hence, there are 2 cases here. The first case is if you get the 2 points from line 1 and the remaining 1 point from line 2. So here we have 1, 2, 3, 4, 5, 6. So you will choose 2 out of these 6, and the remaining 1 point will be taken from this 5. That's why I have 6 combination 2 here and 5 combination 1 here. And by the fundamental counting principle, we have to multiply them. That's 15, by the way. 6C2 is 15. 5C1 is 5. So 15 times 5 is 75 ways for you to have the 2 points here and the 1 point here. But there is also another case. What about if 1 point will be taken from the line 1 and the other 2 points will be taken from line 2? So here we have 6, you will choose 1, so that's 6C1. And from this 5 here, you will choose 2, so that's 5C2. 6 combination 1 simplifies to 6, and 5 combination 2 simplifies to 10. And by the fundamental counting principle, 6 times 10, 60. And since again, we have two different cases, we have to add these. So there are 75 plus 60 or 135 triangles in all. I hope you understood the explanation. So thank you so much, and I wish you all the best for the competition and a great day to one and all.